Welcome, everyone. I'm your host, and today we're building your clinical foundation for optics. We're unpacking the physical behavior of light so you don't just memorize textbook rules, you intuitively understand them for your patients. Approach this explainer not as a list of facts to cram for OCAPs, but as a masterclass in clinical reasoning. We're going to look closely at the ray model of light, which is literally the bedrock of clinical optics. By the end of our time together, you'll know exactly why rays change direction when they hit optically active substances, both in the eye and right there in your exam lane. All right, let's dive in. This explainer is your mental roadmap. Today's agenda covers 1. Light vergence and spherical lenses. 2. Understanding the refractive index. 3. The mechanism of refraction. 4. Snell's law and the normal. And finally, 5. The optics of prisms. Section 1. Light vergence and spherical lenses. Before we get into the weeds, what exactly is light vergence? Seriously, pause and formulate an answer in your head before I say it. Got it? Vergence simply describes what light rays are doing in relation to each other with respect to a given point. Are those rays spreading out? Well, that's divergence. Are they coming together? That's convergence. Or are they running perfectly parallel to one another? Now, if they're parallel, they have a vergence of exactly 0, which, as you know, is the optimal optical state of light entering an emmetropic eye. Here's a foundational mental model you absolutely have to lock in. Plus lenses always force light to converge. We use these all the time to treat our hyperopic patients whose eyes focus light behind the retina, right? Minus lenses, on the other hand, force light to diverge, and that's exactly how we treat myopic patients whose eyes focus light in front of the retina. Literally every refraction you perform in the clinic is built on this absolute truth. Section 2. Understanding the refractive index. So the crucial point we just established is that lenses change the direction of light. But we need to ask why. Why does light change direction in that plus or minus lens in the first place? Well, the answer is beautifully simple. It happens because of optical density. Light slows down when it encounters a substance that is optically more viscous. Think about it like this. You walk a lot slower when you're wading through a swimming pool than you do walking down a hospital hallway, right? Light is the exact same way. It passes more quickly through some substances than others. And how much the light slows down depends entirely on how optically thick the substance is. The reverse is true too, by the way. Light speeds up when exiting an optically dense substance into a thinner one. And this brings us to a massively important metric, the refractive index, or N. It's just a simple ratio. It's the speed of light in a vacuum divided by the speed of light in whatever material you're looking at. Now, here is a classic board trap that I see my PGY2s fall into every single year. Because absolutely nothing in the universe is faster than light in a vacuum, your denominator is always smaller than your numerator. Therefore, N can never, ever be less than 1.0. For practical clinical purposes, we consider the N of air to be exactly 1.0. Okay, take a mental screenshot of this slide. These are high-yield OCAP pearls, and you absolutely must memorize these exact numbers. Water is 1.33, aqueous and vitreous are 1.34, crown glass is 1.52. But look really closely at the cornea here. The actual tissue index is 1.376. So you might be wondering, why do we use 1.3375 for keratometry? Well, it's because that standardized calibration value actually accounts for the negative refractive power of the posterior cornea. Do not confuse the tissue index with the keratometer calibration index on test day. Section 3. The mechanism of refraction. Okay, so we know light changes speed across different indices, but I want to look at the true physical mechanism here. How does a speed change actually lead to a direction change? I really want you to actively think about this. If light simply slows down when it enters dense glass, why doesn't it just keep going straight ahead at a slower pace? How does a change in speed physically force a change in direction to create refraction? Let's look at the physics. This brilliantly illustrates the corpuscular theory of light. I want you to visualize a light ray as individual corpuscles linked together, kind of like a marching band locked arm in arm. When they hit a glass prism at an angle, the corpuscles on one side reach the dense glass first. They hit the mud, so to speak, and slow down immediately. But the corpuscles on the other side are still rushing forward in the fast air. This relative difference in speed pivots the entire ray, and boom, that produces our refraction. This brings us to a massive clinical realization. Refraction requires two distinct things. The ray must pass between substances with different refractive indices, and it must encounter the interface at an angle. If you hit that interface perfectly head-on, the whole marching band hits the mud at the exact same time. There's no relative slowing, there's no pivot, which means zero refraction. This is a foundational rule for everything you do in the clinic. Section 4, Snell's Law and the Normal. Now that we understand the physical mechanism, we can establish the mathematical rules to predict exactly which way the light will bend. To answer that, we introduce the normal. It's simply an imaginary line drawn perfectly perpendicular, a strict 90-degree angle, to the refractive interface. The normal is your anchor. Whether you're looking through a slit lamp or calculating an IOL, it is your central reference point for all optical bending. And here is your classic board rule. When light passes from a material of a lower index, like air, to a higher index, like glass, it slows down and is deflected toward the normal. Exiting into the air, it goes from a higher end to a lower end, speeds up, and is deflected away from the normal. Just remember the mnemonic fast. Faster away, slower toward. Section 5. The Optics of Prisms. Let's tie everything together now, Vergence, refractive index, and Snell's law, into our final clinical application for today. If you trace a light ray through a triangular glass prism, you get this absolutely critical clinical pearl. Real light rays are displaced toward the base, but because our brains project light backward in a straight line, the virtual image the patient sees is displaced toward the apex. Rays to the base, image to the apex. Burn that into your memory, because this is exactly how we measure and treat strabismus deviations in the clinic. Let's test your active recall with a fantastic differential. Think about a rectangular block of glass. It has a high refractive index, just like a triangular prism, right? Take a second. Why do triangular prisms permanently change the direction of light, while rectangular prisms merely displace it laterally, leaving it traveling in the exact same direction it started? Formulate your answer. Well, the answer lies in the geometry of the interface. Snell's law still rules here. When the light enters the rectangular block, it bends toward the normal. But because the opposite side of a rectangle is perfectly parallel to the entry side, the bend away from the normal on exit perfectly cancels out that initial entry bend. The initial refraction is completely reversed. A triangle's sides, however, are not parallel, so the exit refraction compounds the entry refraction, permanently altering the ray's course. I'm going to leave you with this rapid-fire oral board scenario to really test your active recall. You put a base-out prism over a patient's eye to measure an esotropia. Where does the virtual image shift, and what is the exact physical mechanism making that happen? Think about it. If you follow this explainer, you know for sure the image shifts toward the apex, which in this case is inward or nasally. And the physical mechanism? The corpuscles of light hitting the angled glass slow down asymmetrically based on the material's higher refractive index, pivoting the entire ray toward the normal. Master this continuous story of optics and you will never have to guess on exam day. Keep studying and I'll see you next time on The Explainer.